Welcome to the Robotics Brief. I'm Alex.
And I'm Sam. Glad to be here.
Today, we're diving into a collection of papers that, at first glance, seem disparate. Manipulation, memory, 3D vision, agent training. But I think they all point to one underlying truth. The biggest bottlenecks in robotics right now aren't about the raw intelligence of our models, but how we feed them, how we test them, and how we actually make them learn continuously in the real world. It's almost like we've built these incredible engines, but we're still running them on bad fuel or without a proper maintenance schedule.
I can see that, Alex. It's less about breaking new ground in fundamental AI capabilities and more about making the ground we've already broken actually usable for robots that have to, exist outside a lab. Because let's be honest, a lot of what we build is still pretty fragile when it hits the wild, or it's just really, really hard to scale up beyond a very specific controlled demonstration.
Precisely, and that's what makes the timing weird. We're seeing this massive push for foundational models in robotics, which should, in theory, accelerate everything. But then you look at these papers, and they're all tackling infrastructure, evaluation, and data collection issues that frankly feel like problems we should have solved a while ago. It's a bit like building a superhighway without first ensuring all the on-ramps and off-ramps work for normal traffic.
Right. So are we just building bigger, faster cars to drive on the same old broken roads? That's what I'm hearing. Because if the data's biased, or if the training environment doesn't reflect how a robot actually operates, then a bigger model just gives you more confident garbage.
You got it. And that brings us to the first paper, Axis, a growable community-driven data engine for scalable robot manipulation. This one's all about data collection for robot manipulation, but with a twist, browser-based teleoperation and automated task generation.
Okay, so a community-driven data engine. I'm immediately skeptical, Alex. Community-driven usually means unreliable, inconsistent, or full of noisy data. How do you get high-quality demonstrations for something as finicky as robot manipulation from essentially a crowd?
That's the core challenge they're trying to address, Sam. The key is their automated success checking and qualitative assessment, turning those community-collected demonstrations into training-ready data. It's not just upload your video, there's a serious validation layer. They're trying to sidestep the usual reliance on specialized hardware or centralized operators, which are huge bottlenecks for scaling.
But still, browser-based teleoperation for precise manipulation tasks? I'm picturing someone trying to pick up a tiny screw using a trackpad. That sounds like a recipe for frustration and, again, poor data. It's a nice idea for democratizing access, but I just don't see it producing the kind of fine-grained control needed for cutting-edge manipulation.
Well, they're not necessarily aiming for micron-level precision for every task. Think about the sheer volume of diverse demonstrations needed for foundational manipulation models. Even if individual demonstrations aren't perfect, the diversity and quantity could offset some of that. They're also automatically generating new manipulation tasks, which helps with variety. It's a numbers game, in part.
I don't know, Alex. It sounds like they're trading off quality for quantity, and I'm not convinced that's the right trade-off for manipulation, especially when models are so prone to picking up on spurious correlations. If your data's noisy, the model just learns the noise. My concern is that while it makes data collection accessible, it doesn't necessarily make it good or even useful.
I get your skepticism, Sam, but consider this. If they can validate the quality, even if the raw input is a bit rough, then it becomes a question of filtering. And if they can filter effectively, the sheer scale of community contribution could be a game changer for diversity. It means less reliance on a few expert operators doing repetitive, soul-crushing work. It's about opening the floodgates, then putting a smart filter on the other side.
My point is, the smart filter has to be really smart to make up for potentially awful input. That's a huge burden to put on the automated validation. I'm just not seeing a clear path to high-fidelity, generalizable skills from, hey, control this robot with your browser.
It's a valid concern. Let's pivot to a paper that touches on why good data and careful evaluation are so critical. Scale up strategically, learning compositional generalization via bias-aware evaluation and data collection for robotic manipulation. This paper looks at how pre-trained policies take shortcuts, failing to generalize compositionally because they rely on dominant factors rather than truly understanding language instructions.
Now this, Alex, I can absolutely get behind. This is the real issue. You train a policy, it looks like it's working, and then you try to combine two things it's seen separately, and it falls apart. The shortcut problem is endemic. So they're trying to localize the failure to individual instruction factors, like color, verb, object.
Exactly. They're formalizing this idea of instruction factor bias, the tendency for fine-tuned policies to over-rely on dominant factors as shortcuts. They then quantify this through metrics like factor dominance ratio and factor reliance entropy. It's an attempt to diagnose why a model isn't generalizing, not just that it isn't.
Okay, that's smart. Because if you can pinpoint, say, that your model is always over-relying on the object's color rather than the verb in an instruction, then you know where to focus your data collection and training. It gives you a diagnostic tool, rather than just throwing more data at the problem and hoping it sticks, which is what most people do, frankly.
Yeah, it moves us beyond just observing a failure to understanding its root cause. If you ask a robot to pick up the red block, and it only ever picks up red things, you don't know if it understood pick up or block. This framework helps disentangle those factors. It's a strategic way to scale up, as the title implies, by identifying and mitigating biases early.
It reminds me of the classic problem in vision models, where they learn to associate, say, horses with a particular background. Then you put a horse somewhere else, and suddenly it's not a horse anymore. This seems to be applying that same lens to the instruction-following aspect of manipulation, which is a big step, because we need robots to understand put the large blue cube on the small green cone, not just put the blue thing.
Right, and it shows that scaling up isn't just about bigger models or more data. It's about smarter data and smarter evaluation. Because without addressing these biases, larger models just amplify the shortcuts. You get a very confident model that's wrong in predictable ways.
Which, honestly, is worse than a model that knows it doesn't know. You need that humility built in, or at least the tools to diagnose its overconfidence.
Moving on, we have beyond episodic evaluation, memory architectural bottlenecks in sequential embodied question answering. This paper challenges the traditional episodic evaluation of embodied agents, where they solve tasks independently and reset their state, instead proposing sequential evaluation, where agents operate continuously and must retain information.
This is another one that feels like a duh moment, but it's crucial. Real robots don't reset their memories every time they complete a task. They accumulate information. So why are we evaluating them as if they do? It's a fundamental mismatch between how we train and test and how robots actually need to function.
Exactly. They're investigating different memory architectures under these sequential conditions. How do agents accumulate, retain, and selectively reuse information from prior interactions? It's not just about solving one question. It's about solving a sequence of questions, where answers to early questions might inform later ones, or where observations compound.
And I bet they found that standard architectures struggle because they're not designed for this. This is where you see the limitations of models that are built to solve isolated problems. It forces us to think about how memory actually works in a long-running, embodied agent. What's salient? What should be forgotten? How do you manage a persistent, growing knowledge base?
They found that different memory architectures behave quite differently when evaluated sequentially. It highlights the architectural mechanisms needed to support this kind of continuous memory. It's a shift from can it do this task to can it live in this world and continuously learn and adapt.
This speaks directly to the difficulty of real-world deployment. If a robot can't remember what it just did or where it just put something, it's not very useful. You don't want a robot that acts like it has amnesia every 5 minutes. The cognitive load for humans to rebrief it constantly would be immense.
Right. It's about building agents that operate more like continuous learning systems, not just one-off task solvers. And the implications for transfer learning and long-term autonomy are huge. It's not just about the capacity of memory, but its architecture and management.
Which is a whole different ballgame. It means our current benchmarks are likely giving us a skewed picture of actual agent performance. They're good for specific, isolated skills, but not for continuous, real-world operation. We need new metrics, and this paper seems to be pushing in that direction.
Absolutely. For memory, let's look at perception with 3D-aware VLMs with implicit and explicit geometries. This paper tackles the challenge of existing vision language models struggling with 3D tasks, introducing a framework called VLM-IE3D that enhances their 3D spatial awareness using both implicit and explicit 3D geometries learned from RGB videos.
Okay, so this is about getting VLMs to actually understand the world in 3 dimensions, not just a bunch of 2D images mashed together, which is, again, fundamental for robotics. A robot operates in 3D space.
Exactly. They're trying to bridge this gap between 2D visual inputs, which most VLMs are built on, and the need for fine-grained spatial understanding in 3D tasks. VLM-IE3D introduces implicit geometry tokens, which capture high-level geometric priors from videos, and explicit geometry tokens, which encode detailed geometric information.
So they're combining 2 different ways of representing 3D space within the VLM, high-level gist and low-level detail. That makes sense,
because you need both to truly understand a scene: a general sense of depth and object relationships, and then the specifics of shape and size.
Yeah, it's about providing a richer, more accurate representation of the world to the VLM, which in turn should improve its reasoning capabilities for tasks that require fine-grained spatial understanding. Think about a robot trying to fit a specific object into a cluttered space. It needs both the overall geometry and the precise dimensions.
This is critical for manipulation too, Alex. We talked about data earlier, but if your perception module can't accurately perceive the 3D world, then your manipulation policies are going to fail, no matter how good they are in theory. Garbage in, garbage out, and that applies to spatial understanding as well.
Precisely. It's an infrastructural upgrade for perception, making the raw input data itself more robust for 3D reasoning. It means VLMs could potentially move beyond just describing scenes to actually reasoning about actions within those scenes in a spatially intelligent way, which is huge for embodied agents.
I mean, if you want a robot to pick up the red block under the blue ball, it needs to know what under means in 3D, not just relative positions in a 2D image plane. So this seems like a step in the right direction for grounded language understanding.
And finally, we have OpenForgeRL, train harness-native agents in any environment. This paper addresses the challenge of training modern AI agents that rely on complex inference harnesses, like Claude Code or OpenClaw, in an end-to-end fashion with open infrastructure.
Okay, harness native agents. That's a mouthful. So it's about training agents that use these elaborate reasoning and tool use systems, which are currently hard to integrate with standard reinforcement learning setups. Why is that hard?
The issue is that these harnesses are often stateful, multi-process systems. Standard RL SFT stacks aren't designed to natively express that kind of complex, multi-turn inference. So it's tough to get the agent and its harness to train end-to-end, learning from interactions with diverse environments. OpenForgeRL proposes a lightweight proxy that serves the harness's model calls while recording the execution.
So it's essentially a translator or an intermediary that allows the complex harness to talk to the standard training infrastructure, which again feels like an infrastructural problem. We've built these incredibly powerful reasoning agents, but they're siloed from the training environments they need to learn from.
That's it, Sam. It's about making those powerful, complex agents actually trainable in a scalable way. Without this kind of framework, you're either handcrafting prompts and responses, or you're stuck with very limited training scenarios. This opens up the possibility of truly learning from diverse interactions with external systems and environments.
This is crucial for anything involving complex planning, tool use, or even just interacting with APIs. If your agent is going to use a web browser or call a custom function, it needs to learn how to do that effectively through trial and error, not just by being told. And that requires an end-to-end training loop that accounts for the harness itself.
Exactly. It's about closing that loop between sophisticated reasoning capabilities and robust, scalable learning. It means those advanced agents can actually improve through experience, rather than just relying on their initial programming.
And that brings us back to your initial point, doesn't it, Alex? These papers, in their different ways, are all about fixing the plumbing, building better bridges, or laying down proper foundations for the increasingly complex AI systems we're developing. It's not the sexy breakthrough AI announcement, but it's what makes AI actually work in the real world.
It really does, Sam. It's about the infrastructure, the evaluation, and the continuous learning processes that transform brilliant models into robust, reliable, and truly capable robots. The underlying theme is clearly that we need to stop thinking about models in isolation and start designing for continuous interaction with complex, dynamic environments.
And that requires better tools, better data pipelines, and a more honest assessment of how our agents actually behave, beyond just a single task. We need to be critical about how we're scaling up.
So, the question remains, are we ready to invest in the boring but critical infrastructure that will truly unleash the potential of robotics? Or will we keep chasing the next shiny model without building a solid foundation for it to stand on?
My money's on the former, eventually. We have to.
That's it for the Robotics Brief this week.
Thanks for listening, everyone.
See you next episode. Take care.